C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovid's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
All right, good day, folks. Just about to get started here with the formal session for today's webinar. My name is Ari Hakimian. I'm an application scientist here at C-Therm Technologies. Before we jump into the main session here today, just a few housekeeping items. Today's session will be recorded and available for playback after the session. If for whatever reason you need to drop off before the end, or if you have some colleagues that maybe weren't able to make it and you think this would be interesting for them, you can certainly catch the rest of this and share it with anyone after the fact. Also wanted to make note of the Q&A feature today. If you are following along with us and you have any questions related to the work that's being presented, or maybe anything somewhat related to work that you're doing that might be relevant and you wanted to chat with us, you can send those questions in, and we will be doing a formal Q&A session at the end of today's webinar. So if you want to stick around for that, please feel free to do so. All right, we're about a minute past the hour, so I'll go ahead here and jump into the formal introduction. So once again, everybody, welcome. Thank you for joining us today. Our webinar is called the Role of Thermoelectric Materials in Sustainable Building Design. And today it's our pleasure to have a special guest speaker, Dr. Anurag Roy, who's a research fellow at the University of Exeter. He'll be joining us to really be going into this topic in detail. Now, before I pass it over to Dr. Roy, I'll just do a quick little introduction to C-Therm. Wanted to let folks know, maybe if you're unfamiliar with us, if you're new to C-Therm, who we are and what we do. So at C-Therm, we focus on thermal conductivity. We're really experts leading in the transient method class for thermal conductivity characterization. Really, we do so through the advancements of transient methods. And our current platform, our flagship product line, is called Trident. So Trident here, you can see this is a modular system for the measurement of thermal conductivity. We have a variety of methods that are available on this platform, some of which will be discussed in today's session. But really the idea with Trident, the modular aspect of having different methods available under one platform, it's to give you options. One of the challenges we see is related to really taking a good method but applying it in an area it's really not designed for. And this is really embodied quite well in this famous quote from Abraham Maslow: "When all you have is a hammer, everything looks like a nail." So again, with Trident, you're taking more of a toolbox approach, really being able to pick the best option for your task at hand, whether that's related to maybe the sample type that you're working with, a solid versus a liquid. Maybe it's the testing conditions, at temperature, under different pressurized environments, compression. All of these aspects can come into play in defining which is the best method to move forward with. So if you yourself are maybe you're newer to thermal conductivity, or just looking to learn a little bit more in general, we do have a free method selection guide available for download on our website. This guide really covers all of the methods that are available on Trident, plus other options that are available in the industry. So really allow you to compare the different options that are out there. Again, it's a free resource, so feel free to make use of that if that's of interest. I will also mention, so at C-Therm, again, primarily thermal conductivity. That's what we specialize in. But we are partnered with both Rigaku and Metrobib for North American markets, providing Rigaku's thermal analysis line, which covers, dynamic scanning calorimetry, STA, TMA, and those types of instruments. And also with Metrobib for their DMA, for more mechanical analysis. So again, a little bit more variety there in your testing characterization options. Happy to discuss either of these if that are of interest with you. But again, for today's session, we'll be primarily focused around thermal conductivity. I will also mention Thermal Analysis Labs. This is C-Therm's contract testing division. We offer a full variety of testing covering all of the methods that we offer, plus others that are available in industry. So maybe if you're not ready to necessarily bring an instrument in-house, but you're looking for some testing services, we're also happy to accommodate those requests. And just I'll put the offer out there to anyone who's interested. If these methods, thermal conductivity is of interest to you, maybe you want to learn a little bit more as it would relate specifically to your application and your research. You can certainly schedule a technical consultation with us. We'd be able to do more of a one-on-one discussion. Or, maybe if you're just looking for some budgetary information, we could certainly provide some quotation numbers. So I'll end my brief intro here with just a quick client testimonial. This one here is from Daniel Harris at Auburn University, commenting on the use of his C-Therm instrument, which he has been using for kind of noting over 12 years. This would have been one of the previous platform options, I believe TCI. So, commenting it still works great. The device has been a workhorse for us over the years, and it's a real testimony to C-Therm giving the customer their money's worth. So we always like to, share what our clients are saying about us. We do have a variety of testimonials available on our website. If it's of interest, you could certainly go check out and see what people are saying about C-Therm and our products and services. But with that, that brings me really to the end of the introduction here. And as I mentioned, we have a guest speaker here today, Dr. Roy. So at this point, I am my pleasure to introduce Dr. Roy, and please feel free to take over and take us through your content here. So I'm just going to go ahead and stop sharing my slides.
Yeah, thanks, Arya. It's a nice introduction, and welcome everyone. I'm going to share my screen. Hope it's visible.
Yep, you're all good. See it
All good.
perfectly.
Yeah, thanks for the confirmation. Yeah. Hello, everyone. Hi. Welcome to today's webinar, where I'm going to talk about the role of thermoelectric materials in sustainable building design. So here I'm presenting in perspective of a material chemist who is working in engineering lab, specifically renewable engineering lab, where we are working various solar energy applications, including thermoelectricity, and how chemistry, material chemistry, can be a very tricky, a pivotal part to deal with the material design and a sort of applications where we are targeting. As Arya said, I'm Anurag Roy. I'm a research fellow currently working in the Solar Energy Research Group from University of Exeter in UK. And what's in this session is important today, which gonna cover definitely a few stuff. And like thermoelectricity in the current generations, that we know that it's a very important topic where we are struggling to get the renewable energy and, sorting out of the climate change stuff. So let's see how I can cover today's sessions, and which includes what is the thermoelectric, so basic introduction, specifically those who are new to this field, that how thermoelectric systems works. And next, I will move to the why nanostructured material. As I said, I will discuss here in point of material chemistry. So here is the importance of the nanostructured material, that that's importance for the thermoelectricity generation. Followed by why the thermoelectric material is important for built environment, specifically for window glazing systems. And I will show you some real-time examples that how we integrated this thermoelectric material for windows. And next will be our approach for this study, where we have used C-Therm is one of our a key instrument to organize all our study and help us to understand how thermal conductivity is important, a critical parameter to determine its property. And finally, the future of thermoelectric materials, that where we are going and what is the future out of it and how we can deal with them. So before starting the original content of today's study, so I would like to acknowledge my PhD student, Mustafa Al-Fartuz. Actually, this is his work, so all credits goes to Mustafa. He's doing day and night all the work. And thank you so much, Mustafa, for allowing me to share your work here, and a very proud supervisor at the same time. So if you have any specific question or something, feel free to email me or Mustafa. His email address also shared here. And if you want to know more about thermoelectricity and future collaboration, we are here to help. And at the same time, definitely a big thanks to C-Therm, who give me an opportunity to share our results in front of all of you in today's session. Thanks to Mero Scientifics, specifically Felix, who helped me to deal with this C-Therm instrument. And then we jointly applied for a grant through the EPSRC IEEE transitional funding. And when we got this funding, our first target was to get this instrument in, in our lab. So thanks, Felix, for helping out and making a great collaboration and successful project out of it. And yes, so here is our university. You can see in the map that my university, where I'm currently sitting, is based in Cornwall, in southwest of the UK. And this is our lab, where I'm currently working and even sitting. So yes. So who am I? That's very important, why you are here. So before starting a bit more science and thermoelectricity, just a quick introduction of myself. So as I said, I'm a research fellow currently, and I'm also working in the Future 17 SDG program and Global Classroom Mentor in the University of Exeter. I'm also our Environment and Sustainable Institute Early Career Researcher representative. And I joined Exeter as Industrial Impact Fellow in 2019. So it's going to be almost 6 years now in January. And this is my time scale of my journey, that starting, I'm from India. So starting my graduations, post-graduations, then working in Tata Steel in the corrosion department for 1 year, and then PhD, followed by my PDRA, and promoted to research fellow at this moment. So that's a little bit of my academic background. And that's most importantly that what today's intended learning outcomes of today's session. So as I said, that we got understanding some basic thermoelectric nanogenerators, and an overview where we can understand that how the temperature differences, importance to make electrical energy even at a nanoscale level. On the other hand, I'm going to discuss about the role of materials here, specifically for the atomic structure, its electrical and thermal conductivity, as the C-Therm here as a big support of measurement of this thermal conductivity and its thermoelectric efficiency, followed by a few scientific principles based on the Seebeck effect, the figure of merit, and at the same time the phonon scattering of electricity generation, that what is the background of this thermoelectricity generation for a material. Next will be the experimental observation and discussions, where we will deal with how characteristics influence performance and potential improvements for a material. And finally, a practical example that how smart windows and how built environment is very important for thermoelectric generators emplacement. So where I can show you some of our prototype that how smart windows can convert waste heat into the energy and promoting energy efficient buildings. So let's start with today's session about some basic understanding of thermoelectric nanogenerators. So basically, they are promising sustainable energy devices where we can utilize them, using a material. And when we talk about a material here, mostly we are discussing or focusing about nanomaterials, which can convert a temperature gradient into electrical energy. So it's very important to understand there must be a temperature gradient has to be there so that the electrical energy can evolve. Now, compared to the bulk thermoelectric generators that are commercially available, the thermoelectric nanogenerators are more flexible. They are, more power dense, owing their tunable nanostructure, and therefore smaller thermoelectric nanogenerators are better and perfect for small form of application, mostly the electronics and Internet of Things devices and self-power sensors. As you can see in this picture, in the schematic, that there is a hot heat source and a cold heat source, and they are connecting with some conductor. And usually it's an N-type and P-type, two different semiconductors. So the N-type and P-type makes a NP junction, so that when there is a temperature difference between these two end, there is, if we connect with a wire or any type of conduction system, so the current evolves simply. I'm trying to make it as simple as possible. Now, designing of the device is actually controlling where will be your application. So if you want to make the wearable electronics, so we want to make sure the device should be flexible. At the same time, if it is particularly for the solar application, so we need to ensure whether it can be a long-term sustains, there should be no scratches or as stable as possible compared to the outside environment. So accordingly, the design forms. Now, when our design complete and when we get the thermoelectric device is ready, now we have to understand that what is inside there. And if once the temperature gradient formed, there is a heat, there is a hot side, there is a cold side, and when the temperature gradient form, how the heat is transferred or converted to electrical energy. And here comes the importance of phonon. So phonon actually is a part of the solid state physics. So as a chemist, it's still quite challenging area for me to understand, but still it's a very, very important part, or rather say a controlling factor. That's phonons. Mostly there are two types of phonons, one acoustic and one is the optical. So basically the acoustic phonons, which is follow the same path, the in-plane oscillations. So mostly the phonons are the collective oscillations of the atoms. And these oscillations, if it follows the same path in plane, so there's a acoustic, but when it's a cross plane or in a different phases or opposite phases, it's mostly called the optical phonon. Now, these two movement of vibrations, or rather oscillations, is very important to determine whether our thermoelectricity is going to be produced or not, and how much contribution from each of these phonon is coming together to get a high thermoelectric effect. And there are some parameters that we can calculate and we can literally measure, and these calculations is completely depends on this phonons distributions. And again, this phonons distribution is again depends on how the material is designed, whether this material is a nanoform. If it is a nanoform, which shape is the material, what is the crystal structure of the material. So all are basically interlinked, and if we need a very detailed investigation, we need to look every corner out of it. So that's our recent Christmas dinner when we were there. So I got the hot brownie and the vanilla ice cream in the desert. So I thought maybe this is the best example of to show the real-time a relatable example for thermoelectricity. But no, this is definitely not relatable, by the way. But the idea is, if you have a hot brownie and the cold ice cream, any ice cream, not necessarily vanilla. So you can generate power out of it because there is a two different temperature. So there will be a temperature gradient. And as a result, if we can connect each other, it can generate some power out of it. And here you can see an electric power, and that's what the LED bulb lights up. So that's how the system actually works. Now, it's most important that the role of thermoelectric role of the material in thermoelectric applications, and here is the importance of the elements, that which elements we should consider for this application. If we look at the screen, there is a tally between a few specific elements which are actually considered for this particular application. And you can see mostly there are some heavy metals, but at the same time, there are some light metals as well. But the problem is tin, germanium, lead, tellurium, they are very powerful material or elements for this type of application, but at the same time they are very toxic and very harmful for the environment for long-term exposure. And their price is also taking to be considered. So you can see copper, lead, sulfur, iron, zinc, antimony, tin. As long as you go for the actinides and higher atomic level or higher atomic weight elements, they're going to be high price because of their less abundant nature. So that's how here picking up the right element is also important, so that it can be greener and at the same time cost effective. This is basically a timeline that how the different materials evolve throughout 1958 till 2005, that starting from the chalcogenides to the alloying system, followed by doping semiconductors, nanostructure, metal oxide, clathrates. I will discuss clathrates later about that, how it is still potential for future applications. And conductive polymer, this is really interesting, and also the zintal phase. So these are the different crystal structure or different types of material that can be applied for thermoelectric application, and they have a very high potential of getting high current out of a temperature gradient. So it's not necessarily we have to stick with a particular material or particular phase. We can play with around it, maybe 50% of chalcogenides, 20% of metal oxides, and we can make a composite out of it. So that can be another strategy to design a new material for these applications. And when we talk about material, we need to discuss about its properties as well. So there are 4 distinct properties considering the chemical, physical, mechanical, and dimensional. And regarding the chemical, that how acidic it's, how much their corrosionability, their affinity, their electronegativity. Regarding the physical, it's going to be how their conductivity. Thermal conductivity is another important parameter. Electrical conductivity is also important here. Mechanical, so stress, strain, how flexible it is. And dimensional, as I said, the nanostructure formations, that how we can design the structure depends on the synthesis technique. And once we deal with the material, here is a very important thing, that when the TEG performance depends on majorly these 3 categories or these 3 parameters: electrical conductivity, thermal conductivity, and of course nanostructures and its doping. And these all 3 are interrelated to each other, and there is a trade-off at the same time. Like in case of electrical conductivity and thermal conductivity, there is a temperature dominance zone. So they actually control the figure of merit, which is a parameter to determine the thermoelectric efficiency. On the other hand, if we look at the nanostructure and the doping effect and in between electrical conductivity, there is an enhanced due to the polarization effect. For example, if we take a 1D material compared to the 0D, or if we take the 3D or some specific oriented crystal structure, so definitely there is a high chance of polarization effect and high chance of electricity production. And on the other hand, the thermal conductivity and the nanostructure, the difference, the relations between them to reduce phonon scattering, as low as the phonon scattering is there, so that we can reduce the thermal conductivity, and that's a benefit for getting high thermoelectric efficiency. So with this, there are still some unexplored space where we can play with different material and to, control these three parameters: electrical conductivity, thermal conductivity, and nanostructure design. We can select a best material out of it, which can fit between these three parameters equally. So yeah, that's also a challenging area, and many scientists are working on this, that what will be the best. Now, in today's discussion, we are recently published our work in Nature Communication Engineering, where we have used a semi-transparent thermoelectric glazing nanogenerator with aluminium, doped zinc oxide, and copper oxide thin film. As you see from the title, that there is aluminium, doped zinc oxide, and copper iodide. These are very cheap material, easy to synthesize, easy to find out. And but what is the new thing we have done? That is the main thing to discuss. So that I'm going to discuss in a couple of other slides, next slides. This article is available online now, and it is an open access journal. So please have a look and feel free to download anytime. So have a look and share your comments in email or in any other way if you want. So basically what we have done in this paper, we have electrochemically deposited the aluminium doped zinc oxide nanorods. You see, look at the nanorods are here very important. That's, you can see here, the nanorods, this is the ACM picture. So the nanorods over here, and we doped with aluminium. The reason of doping with aluminium to reduce the band gap, and at the same time, aluminium gives a polarization effect. So that you can get NIR absorption at the same time, not a broad absorption, but as a tendency of absorption of aluminium if you dope aluminium in zinc oxide. And yes, so due to this, if we supply heat, the heat-induced phonon scattering reduce the thermal conductivity, and also as it is deposited on the FTO glass, so the charge to carrier mobility is also accelerate. So that's the way. That's why we prefer to go for particularly electrochemical depositions, where the conducting substrate and also the 1D nanostructure, the combination of both two concepts is there, and that ultimately helps to generate the high polarization effect and more electricity out of it. The another thing is the copper iodide. So why there is a two materials? So the aluminium doped zinc oxide here works as an N-type electrode. If you remember the schematic of thermoelectricity, so there is an N-type, there is a P-type. So N-type is basically the aluminium doped zinc oxide, and on the other hand, the P-type is the copper iodide. So the copper iodide thin film fabrication has been proceeded through the sealer method. So it's a successive ionic layer absorption reaction. Sealer is that's the full form. So the sealer method is basically to use a different precursor salt and just dip the FTO into the different precursor salts at different times, so that you can ultimately generate a thin film out of it. Very easy method, but also very easy method to get it some nanomaterials, and eco-friendly at the same time. Not as such wasted, chemical wasted, and health and safety considering. So that's what we choose this things, but there is a problem of this method, and maybe this problem is actually helping us to get the high efficiency out of it, which is called the point defect. So when we go for the Siller method, which is the most chemical method, so they generate the point defect, and due to the point defect, there is a high chance of their property changing. Now, interestingly, as I said, that there is a parameter called the figure of merit. So the figure of merit is basically, we call it ZT, which is actually depends on the three factors again: the reduce the thermal conductivity, increase the Seebeck, and increase the electrical conductivity. So this is the general equation of calculation of figure of merit. As high the figure of merit, as good as your thromoelectricity efficiency. Simple. So it's basically this is the S is the Seebeck, the eta is the your thermal. Sorry, where is that? Yeah, it is the electrical conductivity, T is the temperature difference, and the small k is the thermal conductivity. So thermal conductivity is inversely proportional to your ZT. At the same time, electrical and Seebeck and the temperature gradients is directly proportional to the ZT. And now here is the importance that when we consider of the figure of merit. Okay, before moving to that, so I just need to highlight a few points about that, how we can control these three parameters. So to reduce the thermal conductivity, we can increase the porosity, or we can go for the doping. We can also go for the nanostructuring, pressure alterations, or any complex structure formation. On the other hand, for the increased Seebeck, doping helps a bit. Band engineering and nanostructuring, also the phase transition. And increase electrical conductivity, again, the nanostructuring, phase transitions, and doping. So these are the techniques that we can control all these parameters. And when we talk about mostly the ZT, the figure of merit calculations, so it's basically we need to control the morphology. And when we control the morphology, the terms called the quantum confinement effects comes here. So the quantum confinement effect is actually restrict the particles movement in a 1D and one box system. So that's another complex topic to discuss. But the overall thing is that we need to generate a 1D nanomaterial, or any type of nanomaterial which is mostly highly electron mobility produced and lesser thermal conductivity. So here we have picked out, or we have synthesized 1D nanomaterial, and this 1D material shows a very specific quantum confinement effect, which helps to get the high efficiency of the ZT. This is a schematic where it's an easier way to understand that how the phonons are actually working between hot and cold, and especially into the depletion zone, where the two temperature making a mixture, a cocktail, so that you can see that the nanoparticles is moving here and there, where the grain boundaries, and how it can interact between the short wavelength photon and the mid and long wavelength photon, and hot electron and cold electron interactions. But in another way, that how it is important for the buildings. That's what our future, or that's what our intended application for this type of study. So in buildings, usually, sorry, there's a sensor actually here. So it's in building, how this thermoelectric material or the phonons, whatever we are discussing, is actually helpful. So I'm just giving you the way we can control the building energy efficiency. So first of all, the temperature difference between interior and exterior. For example, the hot roof and the cooler basement. So see, there is some temperature difference generate inside the building. And as I said, if you find anywhere the temperature difference, there is a high chance of electricity productions. And how we can connect this with the building, that's I'm giving you a short sort of example. Another example is the temperature difference between the sunlit and the shaded parts of the building, mostly the windows, and that we can consider for this application. And once again, another one is the climate control in the small specific area, very specific area, such as server rooms or the localized cooling panels and walls and the floors. So when we synthesize our material, we had this is the structure. So this is the morphology. You can see the electrochemically synthesized aluminum dope zinc oxide nanorods. You can see the different types, different magnifications of the nanorods pictures, and these are the copper iodide pictures in the down, and these are the cross-sectional FIBACM image where you can see the thickness and the orientations of the nanorods. Now, if somebody can ask me that your nanorods are, not well distributed in a singular directions, it's quite here and there scattered. The reason because of the synthesis. Here is the importance of the synthesis. So when we choose for chemical synthesis, or rather say wet chemical synthesis, mostly electrochemical depositions or Siller method or Sol-Gel method, so definitely the rods are quite irregular in nature, and they make the rod. That is the good thing, but they are not well aligned. That is why we need to go for the physical depositions methods like the ALD, PVD, this kind of system. But the problem of that system, the controlling of the parameter. So there is some pros, some cons in both synthesis, and also the cost, the time, that is also important factor here. So all has been considered, and then we find that, okay, this is the best thing that we can do in our capacity here. And yes, after that, the copper iodide and AZO. So the AZO is the aluminium zinc oxide here, which is the N type, and copper iodide is the P type. So as we are applying for Windows applications, house applications. So transmission is a big factor here, that our material has to be as highly transmitted as possible, but that's very difficult because when you deposit a thin film, there should be some absorption, there should be some absorption and transmission loss, so that resulting in a semi-transparent nature of our material. And you can see the band gap out of it is approximately say 2.8 for copper iodide, and for the roughly say 3.2 to for the zinc oxide. So that is the band gap, and that is the transmissions data. You can see the visible optical transmissions data, and next is the AFM, which is another parameter to understand the surface density and at the same time the thickness. So roughly here you can see the thickness is more or less same for both copper iodide. So this is the zinc oxide, aluminum doped zinc oxide, and this is the copper iodide thin film, AFM cross-sectional area. A bit of parameter that when the device form, so I have the device at this moment in my hand as a prototype. So this is a device, and you can see here there is an N type, and there is N type, there is a P type. So so the white one is the N type, the aluminum zinc oxide, and the yellow one here is the P type copper iodide. And we measure all the parameters, as I said, which is important to determine the figure of merit. So Seebeck coefficient, electrical conductivity, and power factor. I will come to the thermal conductivity after that, but before that we need to understand these three factors, and that's pretty much a very good results. So that you can see as the temperature increases, the Seebeck decreases. As the temperature increases, the electrical conductivity increases, and the power factor is the overall multiplications of these two parameters, so it's generally increases. So this one is for the zinc oxide, and this one is for the copper iodide, and it's more or less shows almost a similar it's in case of copper iodide and zinc oxide, only the Seebeck coefficient is different because of its conductivity nature. As the Seebeck is getting down, that means it's an N type, and here is the Seebeck is getting up, that means increasing, that means it's a P type. So only the type of different semiconductor, the rest of the things are quite expected, and it shows a similar trend, and that also shows a very high power output. And now here, another important thing is the effect of the substrate. And here as a substrate, we use FTO, fluorine doped tin oxide, the conductive glass. So you can see that how actually FTO helps to promote more electron to get, and that is why you can see that without FTO and with FTO, the change is there is a drastic change and significant change for in both Seebeck and electrical conductivity measurement. So the substrate plays here a very crucial role. If it is a conductive substrate, definitely there is a high contribution out of it. This is the design of our thermoelectric nano generator, and you can see here is a simple measurement, simple design, that this is the hot part, it's the cold part, this is the our material here, and when this is only the hot part, and our material here lens is connected with the two golden probes with the thermocouple so that we can measure it. I have a video so I can share so it can be more easier to understand what is going on there. And there is another, is this the hot, and this is the two part of it. One is the zinc oxide and there is the copper iodide. And the thing is, first we have tried in both hot and cold, two different sources. Then we only put with the hot side. So the cold side in that case considered as the environment. So we literally give a forced heat, the high heat externally, and then the interior, the outer heat, the cold side will be our room temperature, so that we can generate the power. But initially the design was cold and hot together. This is the basic tabulated results. As you can see, for zinc oxide is 1077 Seebeck and the electrical 2100. Now it comes here the thermal conductivity, which is a single parameter we need to measure with the help of the C-Therm. And that's value corresponds to 1.15. Zinc oxide's thermal, aluminum doped zinc oxide thermal conductivity, and for copper iodide it is 1.17. So that represents, that leads to the figure of merit 0.72, 0.72 for zinc oxide and 1.37 for copper iodide respectively. And here is a quick video in our lab where we are using this this C-Therm thermal conductivity meter with the MTPS sensor, so that you can see that this is the copper iodide thin film, the yellow one. So we use this instrument. It's a very handy instrument. We don't need to, get lots of time. We know the previous instrument were quite time taking, and it takes 1 day to 2 days to measure. But now it's very quick. As you can see, we just put the samples and a bit of pressure and with contact with water, and yeah, just turn on the instrument, and the software is quite handy, and you can see there is a measurement going on, and it just takes a couple of minutes, so you can measure up to 20 data at a time, I guess, so that you can make correlations between your data and make an average out of it. So here I'm showing you the only single data at this moment, and for the comparison we always use the substrate. So you can see there is FTO glass as well, so that we can understand what is the exact contribution from the material itself. And this is the way we are measuring, and that's quite handy, very useful, and that's what we are targeting because our material is mostly for the building applications. So thermal conductivity is a very critical parameter to measure for our application, and this is really helpful. And there is as such no size restriction of the samples, but that's a very good point. That's a very good things about that, and we can measure liquids as well. I measure a few my hydrogel, which is the another material where I'm working. So yeah, so that's the thing. So this is how the measurements comes, and you can see this is a copper iodide, which shows roughly the data of here close to 1.17. So yes, so that's the instrument we have, the C-Therm MTPS sensor. Now, I will quickly move to the building fenestration as the energy positive building, why we have particularly selected for building application here, specifically windows. So an energy efficiency in building is controlling by all these parameters. First of all, reducing heating demand, cooling demand, energy use for lighting, and also reducing energy use for the heating water. That's nowadays for winter-based countries is very important. Next is the good housekeeping and people solutions, reducing the energy requirements for ventilations. Now, when we consider the house, so this is a house, for example, and sorry. This is a house, and you can see that how is the heat exchange is ongoing when there is a prototype house, if you are considering it. So it's just the loss of heat. The heat exchange is maximum is going on through the uninsulated walls, and specifically for the windows in that sections. So the loss through of the roofing is about 25%, whereas the loss through the windows and the doors is about 30 to 35%. It depends on the house design, but most of the heat exchange is actually occur through the windows and the walls, but still we can protect the walls through different insulated materials, but it's very difficult for the windows. We can't cover the windows all the time or make black curtains every time. So here is the importance how the transparency of a material, which can at the same time give you a optical, and we call it the visual comfort, and at the same time the thermal comfort. So here is the importance that why we use the window for this type of applications. So the existing technology, novel materials and high risk approach, definitely when we considering it. And here a novel material is very important, that how we can generate a new material which can go both with the existing technology as a easy to the aesthetic appeal, and at the same time all these things can be a high risk approach to through that we can get some high gain results. Quickly overview about the different effects, which is when we considering about a hot side and the cold side. And as I'm not going to the details, this is very popular in thermoelectric materials or thermoelectricity studies, that Peltier effect and the Seebeck effect, and mostly we are talking about here Seebeck effect, but the diagram C is here very important, that where is the N-type semiconductors and how we are designing the nano generator is actually the N-type and the P-type, and the cold side and the hot side. And this is the things I will show you a video that how we can make it so that it can be easy to understand. Another thing of this study is about that the electron flow. So the traditional thermoelectric material and the novel or the emerging material, what is the difference between in these two materials and their electron flows? So you can see in the traditional electron flow, the current and the heat flow in the same general vertical direction. The long current pass through the shunts and the narrow thermoelectric elements. Whereas for the stack based, where we can go for N and P, like a stacking system like this. So the electron flow should be always upwards, always a specific one directions, and there will be less electron loss so that we can get a wide thermoelectric elements out of it. And here also a pie chart which also indicates that how building are actually contributing more carbon emissions compared to the transport industries and agriculture lands and etc. So building also a major source of a major source of carbon emission. They emit a lots of carbon up to 30 to 40% per year. So that is why we need energy efficient building for if we are battle with the climate change. So here is a quick video that how we have generated. So you can see the red one is the N side and the blue one is the P side. And then we make the connections with the thermocouple, and we make the device like this. I have the device with me. I will show you in a couple of minutes. And finally, we get the device and it should like this. So this is our thermoelectric nano generator, where we use this nano generator is able to produce almost one single can produce 3 to 5 nanowatt. So in this case, this is 4, so 12 nanowatt power we can generate out of it. This is an example of that building, and that we used in the windows, as you can see here. So that can generate the power output, the voltage and the current, as you can see in the picture, as we increase the temperature. And then we apply this. It's not just only the power that we can get out of it. It also when there is a heat coming from this way, from the outer side, and your indoor side temperature is also maintaining. For example, if outer temperature say 40 degree or 50 degree, your indoor temperature still remains to 15 to 20 degree. So there is a temperature gradient that they can maintain, and also they have a passive cooling method that can control the indoor temperature. So definitely, as a thermoelectric material, it generates power out of it, but at the same time, another benefit, it can control the room temperature, so can act as a smart window material at the same time. And we tested for 3 consecutive days and to see there is any changes or not. But yes, after 30 days, we have seen there is a power drop. There's a voltage drop actually. So of course the power. So it was initially showing some 16 millivolt voltage out of it. But then it is dropped to almost 7 or 8, almost half, because of the material degradations. So we didn't cover up anything. Without cover, without any type of frame, nothing, no encapsulation, nothing. Fight against moisture or another dust, other factors. These are another study we are ongoing, we are doing right now. But just as a bare, as a basic native prototype, we just tested, and that gives a very impressive results out of it, and very easy method to generate the material, to synthesize, apply, and test it. That's it. We don't need to go for, which is the traditional thermoelectric materials like tellurium, bismuth, which are good, no doubt, but the problem is we can't use for the environment and applications because of their toxicity and also the high price scarcity. So considering every factor together, we have decided to go for the copper and the zinc oxide, which is mostly quite environmental friendly, not so expensive, and that is why there is some little voltage drop due to that. There is another factor here is also the why the voltage drop, because of, as if you remember a couple of previous slides, I mentioned there is a defect. So the point defect is here very important. So when the material loses its point defect due to environmental interaction, it can be moisture, it can be a dust, it can be anything, any environmental factor, the point defect is actually loss. So when the point defect loss, what happens? The electron hopping is actually somehow stop, or maybe the rate of the electron hopping or the mobility is getting decreased, and that is why you can see the voltage drop. It's happened with the solar cells as well if there is no protections. So if we put a solar cells for like a silicon solar cells for without any encapsulating layer or something, the voltage and power will gonna drop because of this. And here is the final things that how we measure. So you can see this is our setup of the thermoelectric measurement. And as you can see, the calibration of N-type thermoelectric. So this is a standard calibration method where we use some ISO standard first to ensure our instrument is well standard to measure our samples next. And then we measure the CBAC for the azido thin film. And as you can see, the two gold probe, if you just remember that, and here is we used two different, you see the two different temperature source. One is the hot side and this is the cold side, and they measured the CBACs accordingly. And I think this is a long video, so I'm just skipping. And at the same time, you can see the power is coming out of it. It's 9.5, 9.4, roughly say, oh, it goes 10 sometimes. So, so here, that's how we checked. And then the device, yeah, so this is a CBAC, and next we measured the electrical conductivity using the 4-probe measurement, so that you can see that how the electrical conductivity and the sheet resistance also coming out of it. And yep, this is the case. So the electrical conductivity of copper iodide. Yeah. Now I'm almost ending my my presentation. So it's just the last slides, that what is the future of materials. So currently we're very excited to working with the clad threads actually. So why clad threads? So these are basically some elemental solid state solutions which give you a metal organic frame structure, like a kind of a porous bulk system, and it's a very heavy porous system. So porosity is a very interesting factor here. So we are thinking to store the heat. It's not just the heat to transfer, it's just to store the heat. For example, what will happen at the night time? What will happen when there is no sun for a long time? So if we store the heat and we can release the heat with a sensor, so for that application, we need to generate the porosity. And for the porosity generations, I think the clad threads are the best options to deal with that. Another thing, if we considering of the environment and we are looking for some natural inspirations, so the biomimicry, I'm also teaching biomimicry here for solar cells. So the biomimicry is another example that what we can get some idea how the nature is actually dealing with it. So the permafrost, which is a kind of ice crystals, which is underground for many years, and they generate some this cage-like structures at -10 degrees Celsius. And how beautiful they are naturally, they make this kind of structure naturally at -10. So this is some inspiration. And in this map, you can see the violet, the purple area is where the natural permafrost can found. Mostly the Arctic circles and Arctic zones and the Himalayas zones. And that's very interesting that this natural water can make this kind of structure at -10 degree underground. Another example is that how we can make a nanostructured material out of it. And the great example is the penguin feeder. So the penguin's feeder, if we look that if their structure, their orientation, their distribution is, if we can picking and mimicking in lab, that's will be really, really interesting things to consider. And the last but not the least, the seaweed and some sea sponges. Their structure is also helpful, their porosity and how they conduct, they reduce the thermal conductivity actually because of the undersea. It's a very freezing freezing temperature, and still they are maintaining their life there. So that will be an interesting to understand this type of material. With this, thank you very much for your kind attentions, and I'm happy to answer if you have any questions. And have a lovely Christmas and New Year.